Our presenter today is Ron Klemencic. I've been chatting to Ron probably since January this year about possibly application of this structural system for a job in New Zealand. Ron is chairman and CEO of Magnuson Klemencic Associates, MKA in Seattle, based structural and civil engineering firm. He led the development of the structural system, including performance-based seismic design, performance-based wind design, and structural fire design. He'll be touching on two recent completed projects, Rainier Square in Seattle and 200 Park Ave in San Jose. By using the system in Rainier Square, they were able to save 10 months in construction program, and at 200 Park Ave, approximately 10 million in cost savings, along with a 3-month reduction schedule. So that's a brief introduction on Ron and what he's going to present. I'll hand it over now to Ron.
Great. Thank you, Keyshawn. And thank you, everyone, for your interest today. I hope to share with you our experiences and some good success that we've achieved over the last number of years. I'm going to start out with that in context of a specific project, Rainier Square, and then we'll move on to some other projects that are completed and ongoing. So Rainier Square is located in Seattle, Washington. It's a very tall, slender building. The developer of this building was Wright Runstead and Company, which is a prolific development company in the Pacific Northwest of the U.S. You can see the architect and the general contractor. Some of the statistics about this project, just to set context of what the building is itself, 1.4 million square feet. It's very tall and thin. You can see the statistics here. And it does have 7 levels below grade, so we have a quite deep basement. The typical floor plans for the building are typical of many buildings that we see designed and built around the world. Here you see a typical low-rise office floor plate, and in red color is the core. When we originally designed this building, the core was conceived as a traditional reinforced concrete core. And the dimensions of the core were nominally 12 meters wide by 30 meters long. So each one of the cells of the core, 3 in number here, you see would be 12 by 10 times 3. As the building extends upward, the form of the building tapers down, and so does the core. So here the core is down to 2 cells, and it's now 12 by 20. And then at the very top of the building converts from office use to residential use, and the core itself is very small now. It's 12 meters by 10 meters. That core alone was not stiff enough to brace the building with the reinforced concrete core, or as we'll also find with the SpeedCore technology. So it needed to be supplemented with an outrigger system, very traditional diagram you see here with the multi-story outrigger trusses and belt trusses that are located about 2/3 of the way up the height of the tower. This is at the transition between the office below and the residential above. These floors were used for mechanical services and amenity floors for the residential. So diagrammatically, this building, I'd say, is very traditional in terms of its structural arrangement and the bracing arrangement, and a building that we've designed and built similarly around the world in a number of locations. Of course, when we zoom in and look at the outrigger and belt trusses, this is a fairly complex piece of construction to execute. In particular, the connectivity between the outrigger trusses and what was originally conceived as a reinforced concrete core. That load transfer from steel to concrete is quite complex, involving substantial embedded steel elements, which substantially slows down the construction at this location. Traditionally, this is the kind of building we've built around the world for decades now, where we've got a leading reinforced concrete core, typically built with a jump form, occasionally with a slip form, typically with a jump form, and that formwork is sent out way in advance of the steel erection, mainly due to the cycle times of both. It's typical in the US for the jump form core to move forward at the rate of about 1 floor per week, whereas the steel construction can be erected at the rate of 2 to 3 to sometimes even 4 floors per week. So this lag between those two operations was really the original problem statement that we took on as a challenge to try to figure out a different way to conceive the structure in order to squeeze this time lag out of the overall construction program. The idea in itself in the beginning was something that was entitled a concrete-filled composite plate shear wall. You see the letters on the upper left. Concrete-filled composite plate shear wall. Later, the American Institute of Steel Construction, AISC, named this system SpeedCore because it's able to be erected so quickly. Its basic components are fundamentally these prefabricated modular wall panels. Here you see a wall panel that's 1 story tall. In the case of Rainier Square, it was about 4 meters tall and 1 bay long. In the case of Rainier Square, 10 to 12 meters long. And these panels are prefabricated in the shop, 2 steel plates interconnected by a field of cross-tie rods. And those cross-tie rods serve many functions, and which we'll talk about in more detail here in a moment. So this is a typical wall panel. A second typical wall panel was one that included the coupling beams or link beams. And the idea was to prefabricate these in the shop as well to take the construction of the coupling beams out of the field and put them in the shop. So these H-shaped panels were also prefabricated along with the coupling beam and erected as a single piece. Looking in plan view, what you see here are 2 plates interconnected by cross-tie rods. In the case of Rainier Square, the cross-tie rods were spaced at 300 millimeters on center, both horizontally and vertically. And working from left to right on this image, you'll notice a number of different ways you might conceive connecting those cross-tie rods to the plates. Leftmost, you see a double nut configuration. Moving to the right, then an inside fillet with a double nut, an inside fillet with a plug weld, and then the rightmost image where the rods protrude through the wall plates and there's an outside fillet weld. All 4 of these configurations of connectivity are viable engineering solutions. The question was put to the steel fabricator, which did they prefer, which could they fabricate most efficiently, most cost effectively, and with the highest quality. And in the buildings that we've built so far to date, all the fabricators have chosen the methodology on the right. That's one of the critical details to sort out in designing this system. In the case of Rainier Square, there were 240,000 cross-tie rods, so 480,000 connections to be made. And if you can make each one of those connections 1 minute faster, 1 minute better, you can imagine the time savings on the fabrication side. Another critical detail, and you see it most clearly on the right side of this image, is the field splice from panel to panel. In this case, you're looking at a welded splice, a horizontal welded splice that is configured with a partial penetration weld and a reinforcing fillet. And the design objective of this connection was to develop the full tensile strength of the plate, as we're designing for high seismic demands in Seattle. And we wanted to ensure that the plate would yield and strain harden before the weld itself would fail. This weld in particular was pre-qualified through testing and proven to work to meet that criteria. Another way to splice these plates, though, is to consider a bolted splice. In this case, you see a detail with a blind bolt configuration, where on the inside of the plates, there's a nut that's pre-welded to the inside of the doubler plate. And then in the field, the bolt is passed through the outer plate to bolt the sections together. Either one of these connection methodologies also satisfied the engineering demands. And this is, once again, was put to the fabricators and the erectors as to their preference. In all instances to date, the field erectors have chosen to weld. And they chose to weld mainly out of concern of bolt hole alignment, until our most recent project, which I'll share with you at the end of this presentation, which is being currently constructed in Boston, where they are in fact field bolting. How the system was assembled in the field was first the corners of the core, in this case 8 corners, were prefabricated as box columns. And those box columns, those box columns were made of a similar type of construction of steel plates and cross-tie rods. Those box columns were configured in 2-story high lifts and then infilled with wall panels to complete the configuration of the core. You can see in red color the link beams that were included in the prefabricated panels. When we first rolled out this idea and started designing this building, you'll see this is Engineering News Record magazine in 2018. There was a lot of skepticism in the market about adopting a new system that had never been built before, never been implemented on any project. And so the title Calculated Risks was, I suppose, appropriate. But I will say, given the amount of attention to detail and rigor that was put into the design and the planning by the contractor, the fabricator, and the erector, the risks were indeed calculated in the sense that we had sorted through pretty much all of the details before we went live with construction. Long before any of that took place, dating back to the early 2000s, 2005, in fact, the Charles Pankow Foundation, the MKA Foundation, and Purdue University launched a research effort where we started to test this system in the laboratory. This is Professor Mark Bowman and Mike Krager in the Bowen lab at Purdue University. On there, to the right of Mike Krager, you see a 5-story tall T-shaped wall specimen, one of the early specimens that we tested in around 2008. So dating back to the mid to late 2000s, we were in the laboratory testing. In particular, testing all configurations. This case, you're looking at a SpeedCore module before it has been concreted. And this particular test was looking at what is the buckling strength of that unconcreted wall module, so that we could understand how far in advance could we erect steel, floor beams, and metal deck before we needed to place concrete inside the wall panel for stability and strength. So this was looking specifically at the buckling strength of the unconcreted wall. Professor Amit Varma at Purdue and his team have also done a decade's worth of research looking at all sorts of different items. Here you see a stack of different cross-tie configurations, looking at cross-ties passing through, supplemented in some cases by headed studs, in other cases headed studs alone, but looking at all the different variables and testing them. In parallel, we had another research team at New York University in Buffalo. This is Michel Bruneau and his research team, testing mostly bolted connections on very large scale specimens. Here you see one of those test specimens and the bolted field splice that was tested. The T-shaped section looking at a vertical splice. Here it's laid horizontally, but again, these are specimens that were tested at SUNY Buffalo, looking primarily at bolted splices. Before we started construction of any buildings, we also built full-scale mock-ups, two of them, in fact, for Rainier Square. The first one being a formwork configuration with wooden formwork and plastic PVC cross ties. And the purpose of this mock-up was to primarily investigate concrete placement, specifically the placeability, flowability, consolidation, and the performance of the concrete mix itself. And in putting it in a wooden formwork, as we did, we were able to not only witness the concrete placement, but then we were able to easily strip the formwork and verify the consolidation and the flowability and the lack of cold joints, and convince ourselves that our mix design was achieving the construction objectives that we set out. In addition, we used this mock-up to test all of the mechanical properties of the concrete mix, including strength, modulus, shrinkage, heat of hydration, etc., to prove out to ourselves that we had the appropriate mix design. In addition to the concrete mock-up, we built a full-scale steel mock-up. In this case, the elements were fabricated in a shop in Portland, Oregon. Here you see one of the corner columns or box columns being fabricated. The circular holes that you see in the side plate of the column is an inside plate for the wall, which allows the concrete to flow through the wall panel and around the corner. These elements were fabricated and placed on a truck, shipped from Portland, Oregon, up to a yard outside of Seattle, where the erection crew then practiced handling and erecting these very large panels. You can see what the two construction workers on the right-hand side there, some of the scale of these panels are quite large. This practice by the erection team was invaluable. They learned very good techniques on how to tip the panels off the truck, how to handle them in the air, and then how to set them and position them effectively in the field. So we built the full-scale mock-up in the yard about 2 miles from the site, inclusive of experimenting with the field splice, whether that be hand welded or mechanically welded. The project then moved into a traditional shop drawing phase. Here you see just a typical shop drawing, and included in those shop drawings are the typical panels. What you'll notice in this particular image is included with the H-shaped panel are also all those connection materials necessary to receive the incoming metal deck. So you see the deck ledger angle, and you also see the shear tabs for the incoming steel beams that will be connected to the wall. Everything that was to be connected to the wall had its connection materials shop fabricated and installed. So this panel would arrive on site, ready to receive everything incoming. Similarly, mechanical penetrations were pre-coordinated, and in this case, this large-scale opening required a doubler plate and some inside strengthening plates in order to create the shear flow around the opening. All this was done in advance, so that when the trucks arrived to site and erection began, all the parts could be installed very quickly and efficiently. This is the very first panel that's being lifted off the truck and lowered down into the excavation. At the base of the excavation, the first lift of the walls was supported on a series of columns. Those columns were embedded into a 3.5 meter thick raft foundation. In Seattle, the soil conditions are quite good, and so there's no need for piling. All of this is on a shallow raft foundation, but to create the load transfer from the core wall above to the raft below, that was done through these columns or stanchions, as we called them. Here you see on the stanchions a slew of metals or Nelson studs that are welded to the sides of the columns to help facilitate the load transfer. You also see the bottom layers of reinforcing steel in the raft and some of the vertical shear reinforcing steel on the left-hand side. Of course, the top layers of reinforcing steel of the raft are yet to be installed. As the building started to rise and be erected, here you see the 2-story tall box columns on the corners and the one-story tall, excuse me, wall panels that have been installed. Looking closely at the core or at the corner columns, you see some circular holes. Those are holes that are placing ports for the reinforced or for the concrete that is then placed later, being pumped into those holes and being placed in a downward fashion, one floor at a time. As the building was erected vertically, notably, you see how close the erection of the uppermost core is with regards to where the steel beams and floor decking are being installed. It's roughly 2 floors. In total, the sequence of events included the core erection being leading the steel floor beam erection by about 2 floors. You see the steel beams and metal decking being installed. About 6 floors, 6 to 8 floors below this is where the concrete was then being pumped into the core in a trailing operation. And an additional 4 floors below that is where the concrete was being placed on the metal deck. So from the uppermost erection floor of the core to where the floor slabs were completed and concreted, there was about a 12-floor gap between those two operations. And it proceeded upwards in that fashion over the height of the tower. Looking closely at the core again, you see the circular holes in the sides of the corner columns, which are the placing ports. And if you look closely at the link beams, on the tops of the link beams, you'll see what we'll call blow holes. These were holes that allowed us to visually confirm that the concrete had flowed into the link beam and it had filled the link beam in total as the concrete began to spill out of those holes. The outrigger trusses that were included in the design were connected back to the core on very large scale connections that were all shop fabricated as part of the panel construction. So this took all of that complicated connection activity from the field and put it in the shop. So both at the core and also at the perimeter outrigger columns, all of the gusset plates and connection materials were shop fabricated, which allowed the field installation of the truss itself to be very simple and bolted connections. The final configuration of the outrigger trusses and belt trusses you see here included both wide flange shapes in green color, and on the right-hand side in gray color, you see the circular buckling restrained brace, which was part of the seismic design of the tower, acting as a fuse to absorb some of the seismic energy. These are very large-scale pieces, but were very easily installed with bolted connections, while all of the heavy fabrication was done in a shop. The topping out of the final beam of the project happened exactly 10 months to the day from the day we set the first panel at basement -7. So from basement -7 to the roof, which was level 59, So 66 floors of steel construction completed in exactly 10 months from the day we started to the day we finished. Overall, the project was completed 10 months sooner than was otherwise predicted from the original schedule. The original schedule being based on a reinforced concrete core and reinforced concrete floor slabs below grade in the garage, compared to what we built, which was SpeedCore and steel floor framing in the below grade garage. The original schedule was 32 months to complete the building. We completed the building in 22 months, a savings of 10 months in total. One question that comes up with regularity is, what did you do about fire protection? In the case of Rainier Square, because at that time when we were designing and building the building, we had not yet completed any fire testing. For Rainier Square, the core walls are spray fireproofed with monocoat spray-on fireproofing. During the construction of Rainier Square and subsequent to its construction, we have completed very rigorous fire testing in the lab at Purdue. There is this research report I'm showing you the cover of that basically documents the fact that within certain design parameters, being wall thickness, plate thickness, and cross tie spacing, that you can justify the elimination of spray-on fireproofing to achieve a 3-hour or a 4-hour fire rating. This work is completed and has informed now our subsequent projects where we are building the buildings with no spray-on fireproofing for the walls. Which leads me to the next project. This building is in San Jose, California, very high seismic territory, about 5 miles from the San Andreas Fault. It's a 19-story office building. In plan view, it's a very large floor plate. The floors themselves are about 5,000 square meters per floor. In red color, you see the seismic bracing system for this building. It includes 2 independent cores, a single cell core down in the lower portion of the image, and a 2-celled core in the upper portion of the image. Again, each cell of this core is about 12 meters wide and 10 meters long. Once again, we built full-scale mock-ups with the contractor. In the case of this building, it was a completely different general contractor, different fabricator, different erector, so all new to them again. They too will tell you that the mock-up was invaluable in terms of understanding how to build and handle and erect these pieces. My colleague Russell Larson, standing next to the connection of the first wall panel. This is during COVID, so he's wearing a mask. But you can see the very substantial connection between the first lift of SpeedCore wall panel above and what is a reinforced concrete shear wall to be cast below. The building's now completed. It's an office building, no residential at all. It's 100% office over parking. And this building was completed 3 months faster than if it was an otherwise reinforced concrete core. Another item to note on this building, given the high seismicity of the site, both its proximity to the San Andreas Fault and the fact that the soil conditions at this site were very poor, the seismic demands on this site were very, very high, resulting in a reinforced concrete core wall that would have been nearly 2 meters thick for a 19-story building in order to manage the shear stresses. Whereas in SpeedCore, because of the substantial shear strength of the plate, we were able to reduce the wall thickness from 2 meters down to 1.2 meters at its thickest portion in the base of this building. The third building I'll share with you is a building currently under construction in Cambridge, Massachusetts, 75 Broadway. This building is a 19-story laboratory building for MIT University. In plan view, it's different from what we've experienced on our other projects. What you see in green color are SpeedCore planar wall panels, whereas the elements you see in yellow color are typical concentrically braced steel frames. So in this case, the SpeedCore wall panels were used for their superior stiffness in the transverse direction, whereas in the longitudinal direction, there was no need for that additional stiffness, and the concentrically braced steel frames would suffice. This is the configuration of those typical steel braced frames. This is a wall elevation of the SpeedCore wall panel. Something to note here is the small circles that you see in this diagram at the base of each wall panel are vent holes placed or drilled in the wall panel to allow during a fire event for any unreacted water inside the wall that's part of the concrete placement to vent steam during the fire event. The guidance for the size and spacing of those holes is included in the research report that we published as part of our fire testing. Typical shop drawings were prepared, 1-story tall wall panels typical, inclusive of door openings and mechanical openings as they need to be. A little different end of wall configuration. In this case, you're looking at a plan view of the wall panel with the cross ties. And the end condition in this case is a wide flange column with some tabs welded to it to accept the incoming wall panel in order to plumb and through the wall panel. This building is being built with bolted steel splices. In particular, the erectors chosen to bolt the vertical splices and to weld the horizontal splices. Once again, either of those configurations would work from an engineering point of view, and we gave the choice to the steel erector, and he's chosen to build the building using bolted vertical splices and welded horizontal splices. This is just a close-up of that bolted vertical splice and its connection to the boundary element column. In the shop, the bolted splices were prefabricated using these shuriken nuts, or blind bolts as it would be. These nuts are pre-welded onto the inside face of the plates of the wall. And then as the wall panels are erected, this was just a test fit up in the shop to ensure bolt hole alignment, to be sure all things fit together as intended. Moving out into the field, and this building is under construction as we speak. This picture was taken about 2 weeks ago. And what you're looking at here is that corner end column or boundary column on the wall panel. You see the column splice itself, which is all bolted and fairly typical. To the right of the column splice, you see the wall panel. Its cross ties protruding through the wall panel, but then looking more closely, you can see the field bolts that are then holding the wall panel to the connection material to the column. This is the back side of the same panel. Once again, you see the vertical bolted splice and a side view of the same column splice connection. In a few instances with large door openings, the wall panel is connected to the column at a door opening. Once again, you see the vertical bolted splice to the boundary column. The horizontal splices are being made on this project with a track welder. So in this diagram, or this is photograph, what you see, the yellow colored device is the actual mechanically moving piece that moves the welding arm, which is protruding below it, that makes the horizontal weld across the panel. and it rides on that aluminum track that you see it connected to. This particular splice happened to be off the floor a fair distance, so the contractor built a temporary scaffold for the operator of the track welder to stand on while he operates the track welder. The track welder on this project is operating at the rate of about 12 meters of weld per hour. So each one of these field pass weld. So in order to complete the entire field splice, it takes about 3 hours of work with the track welder to complete the final horizontal splice. The connection of the floor slabs back to the core wall ultimately are made in most cases with rebar dowels that are inserted into pre-drilled holes in the wall. You see here the pre-drilled holes just above the top of the metal deck. Ultimately, rebar is inserted into those holes and mastic is placed to keep the wet concrete inside the core wall when it's concreted. But this is how the shear connection is made between the reinforced concrete slab or slab on metal deck and the core wall itself. The mechanical penetrations, once again, were pre-coordinated and prefabricated in the shop, as were all the connection materials to receive the incoming floor beams. The placing ports were similar to our past projects as well for the incoming later to be placed concrete. As well, you see the deck ledger angle there to receive incoming metal deck. This building, when I was there about 2 weeks ago, they were up to level 4 in erection. I'm actually on my way to Boston again this week, and I think they'll be up to level 7 or 8, predicted to be completed by the 1st of September. Once again, as compared to a reinforced concrete core, I believe on this building, they're going to save about 3 months of scheduled time. That completes my formal presentation. I'm sure there are many questions. Happy to entertain them. Before we jump into the questions, I will say one or two other items. First, this system, when we designed it originally, was not in the US code. So our path of travel for approvals was to point to the alternative means and methods provision and demonstrate through engineering subjected to third-party review that we complied with the intention of the code. That's how we achieved our original approvals. Subsequent to that, this system now is recognized in the US codes. It's in the AISC specification as a recognized system, inclusive of response modification factors and overstrength factors, etc. The other item of note is this is a non-proprietary system. There is no patent, there is no copyright. I don't own it. This is something that we all as practitioners are able to use and employ in our designs. It's certainly not the solution for every building, but it is a good solution for some. And so I'm hoping that you at least are intrigued to learn more and perhaps think about it on one of your future projects. And so with that, I'll pause, and Keyshawn, I'll ask you and see if there are some questions to open some dialogue.
Thanks, Ron. Much appreciated. Yeah, there's quite a few questions. Probably the first one I'll start off is maybe if you could touch on the design guide that you've helped develop for the system.
Sure. So via the AISC website, you can gain access to a design guide that details out the procedures and methods to effectively design this system. The design guide was written by ourselves and all the researchers that were involved, so it's inclusive of kind of all of the state-of-the-art knowledge. I will say it is a prescriptive document, and as such, it has certain conservatisms built into it. And depending on how you were to choose to design and your method to designing, in the US, for example, if we go through the rigors of a nonlinear response history analysis for seismic and perhaps even for wind, we can relax some of those prescriptive requirements that are written in that design guide. Either way, there is guidance via AISC's published document. In addition, there's a full library of publicly available research documents. All of the research that we've done for the last 20 years is published. You can access that through a number of portals. The one that's probably most direct is through the Charles Pankow Foundation website. So if you were to go to pankowfoundation.org, it's PANKOW, pankowfoundation.org. All the research reports are published there and are downloadable for free.
Awesome. Thanks, Ron. Another question. Over time, how much do you think the axial load share between concrete and steel will migrate to the steel plates due to creep and shrinkage? And do you deem that to be significant?
Good question. So a couple of items of note that let me go off on a little bit of a tangent for a moment, but I'll come back to the question. So I failed to talk specifically about the cross ties, but let's talk about that for a moment. Their role is very important in the system. So first, the cross ties help facilitate the modular construction of the panels. So that's kind of, we'll call it design objective number one, to help facilitate the prefabrication of the units. Those also help stabilize the panel during transport and erection. Next, as the panel's erected, it keeps the plate from buckling under erection loads, so it gives us strength to advance the steel construction some numbers of floors above where the concreting operation is because it controls the plate buckling. Once the concreting operation is begun in the wall, the cross tie rods prevent the wall panels, again, from buckling under the hydrostatic pressure. So they serve to resist, like a cross tie in a formwork system, resist the hydrostatic pressure. Ultimately, they serve as a mechanical shear transfer mechanism between the steel and the concrete for exactly that, the load sharing of the composite construction. And then finally, they serve to confine the concrete, much as hoops and ties do in reinforced concrete construction. The cross ties in this case restrain the plate and create a confined concrete condition that improves the performance of the concrete. Choosing the size and the spacing of those cross ties is a design parameter. And if you then keep all of those objectives in mind, you can make design choices on the size and spacing of the cross ties. All right, so all of that said, back to the question on the creep and shrinkage. The analogy that I'll offer to you is if you think about it in the context of a reinforced concrete wall with rebar inside the wall and the concrete around that, of course, the same phenomenon essentially exists. It's a mechanical transfer between the two materials, in that case, through the bond strength and the nubs on the rebar to connect the two together. In the case of SpeedCore, that reinforcing steel just happens to be on the outside rather than the inside. And most simply put, if you do the calculation to look at steel equivalency, what you'll find is the equivalency in reinforcing steel is a very, very, very heavily reinforced RC wall to the tune of number 32 bars at 300 millimeters on center, 4 layers of them. That would be the equivalency of one SpeedCore panel. So with all of that said, that amount of steel restraining the creep and shrinkage of the concrete actually improves the overall shrinkage and creep behavior in time. The load sharing is always there. We've gone through testing of that over the years and convinced ourselves that, in fact, it's not worse. In fact, it's better than reinforced concrete.
Thanks, Ron. Another question everyone's always keen to understand is what's the cost comparison between this and when for Rainier you started with the traditional RC core and talk about there's aspects of the build cost, but then there's
Yeah.
all those other cost financing and
Yes.
with the program
Yeah.
savings.
So the cost question is a complex one. I'll try and break it down into some simple parts. Um, Perhaps most notably is our experience to date is that the fabricating and erection markets subcontractors by and large don't quite yet know how to price this because they haven't built many of them. And so the range of prices we've seen in the market amongst competing erectors and fabricators has been a very wide range because to some degree they're guessing because of the lack of experience. That sounds a little frightening. At the end of the day, they've all turned out very well, but don't be surprised if you entertain the system and go to market to price it that you find a wide range of prices. I believe it's simply because of the lack of experience. On the projects that we've built to date, the prices have come in the end at either equivalent to reinforced concrete walls, to somewhat cheaper, to somewhat more. And again, that underscores what I just mentioned about the market's lack of experience in pricing the system. What has been 100% the experience is the speed savings, the time savings. In each case, you can characterize it in terms of numbers of months, but maybe better to characterize it in percentage. In all cases, we've saved 30% on the structural construction schedule. The construction schedule was reduced by 30%. So if you figure that the cost of financing and the improved cash flow for rent for the client, if the building is delivered that much faster, those two numbers alone probably eclipse any hard cost premium that you might experience in the actual fabrication or erection.
Thanks, Ron.
I
Um,
will I will go
oh,
off on a little bit of a tangent just for a moment, because it's just something that comes up regularly. Our examples to date are a very tall building and some fairly mid-height buildings. What about other buildings? And the truth is we've been studying the system for a whole variety of different applications, everything from wind turbine masts to vulcanizing towers to sports stadiums, and currently we're designing 2 hospitals using this system. So it's not simply for use in a high-rise office building. It can be applied to any building in the right circumstance.
thanks, Ron. Um, how do you manage the ductility of this structure as a composite core wall system? What ductility did you use for, say, Rainier Square, and what ductility can this system achieve?
To give you a very precise answer to the ductility question, I'd refer you to the detailed research reports where we have gone to extreme measures in testing them. The system itself is very ductile. For all of the buildings that we've designed to date, considering seismic demands, in all instances, we've gone to the rigor of nonlinear response history analysis, foregoing any type of response modification factors and prescriptive code level design, if you will. Everything has been done with a performance-based design methodology, specifically interrogating the strain demands on the wall. In all cases, the strain demands have been quite modest. The wall itself is very robust. That all said, in the US, the system has gone through the rigors of what's called a P695 study, which is a very rigorous parametric study of wall configurations aiming to define an R value, a response modification factor value, which for a coupled wall system in our code now is 8, which is the equivalency of a special moment frame building and or a special reinforced concrete shear wall building. So on a comparative system basis, it's been proven to be as ductile or better than the most ductile systems in our code. And all of that research is, again, published and available for your review.
Thanks, Ron. Another question, I think you did touch on it during the presentation. Consolidation of the concrete achieved and verified. You obviously had those mock-ups with the timber shutters. But maybe touch on the mix design to
Sure.
because it was mainly around the mix design. Yeah.
Yeah, so the mix design, go back here. The mix design itself, we experimented with quite a bit, looking at pumpability because Rainier Square is 270 meters tall, so we needed to pump the concrete a great distance vertically. We thought about, do we place the concrete in a downward fashion as you see in this image, or do we place it in an upward fashion through guillotine valves and pump the wall full from the bottom up? All of these things were considered. At the end, where we ended in all cases is we're placing the concrete in a downward fashion, one floor at a time. The mix itself is much more like a grout than it is concrete, meaning there's no coarse aggregate. It's sand, cement, and some chemicals to enhance the flowability. The strength of the material is about 70 MPa. So it's not crazy high, but it's high strength. It's not needed to be high strength for any other reasons than stiffness demand. In the case of Rainier Square, the tower design was controlled by stiffness. And so we were seeking a modulus value for the concrete more than we were strength. But at the end of the day, as I mentioned, the mix design itself was more of a grout, 70 MPa grout. And we did verify all of the engineering parameters like modulus and shrinkage and creep and heat of hydration, etc. So it all met our objectives.
Thanks, Ron. How do you justify the composite action between the concrete core and the steel plates under cyclic loading, and what failure mode governs that interaction? Presumably, it's all to do with the ties.
Yeah, so the ultimate failure mode of this system is plate buckling, and that helps define the cross tie size and spacing and plate thickness. You can tune those up or down depending on your demand levels, but the ultimate failure mode is plate buckling under compression and shear. All of this, again, is documented in the research reports. And so as we design these systems, we're looking to stay away from that particular failure mode with proper sizing. I think that answered the question.
Yep. And what software did you use to do the seismic analysis? And probably run through the peer review process around this as well, particularly if it was Rainier Square
Sure.
first time done. Yeah.
Yeah, so the software tool that we have commonly used is ETABS. ETABS these days now has a nonlinear response history analysis module to it. It didn't used to, but ETABS bought RAM Perform and incorporated into the ETABS software itself. So when we started this 20 years ago, we were using a software called Drain 2D, and then we used Drain 3D, and then we used Perform, and then we used RAM Perform, and now these days we use ETABS. But essentially, I'd say any software that can do an adequate job of nonlinear response history analysis using fiber elements. So these walls are modeled with fibers as fiber elements in kind of a layered fashion. And so that's how we go about our analyses. Regarding the peer review process, on all of our projects to date, they've gone through a pretty rigorous third-party peer review. On the Rainier Square project, which was the first project, that was reviewed in particular by Jim Malley, who is a notable steel designer in the United States, and Ron Hamburger, who used to be prior chair of ASCE 7. So in terms of the scrutiny, it was scrutinized by two of the most prominent structural engineers in the United States, in addition to the building authority having their own in-house review. In addition to Ron Hamburger and Jim Malley, they brought in to help on the peer review side, Michel Bruneau, who was one of the researchers conducting the research at New York University in Buffalo.
Thanks, Ron. And then probably one that maybe you went over quickly is the at the bottom, the base of this core. How do you effectively jump it, and how do you tie it into the raft? And
Right. So at the base of the core, let me see if I can go there quickly. There. Keishan, are you able to see that image?
yeah,
Yeah, so at the base of Rainier Square, we use this method, which was, you can see if you look very closely, these vertical columns were attached to the first lift of the core wall, the SpeedCore wall, with bolts. You can see the bolts on the outside of the plate. And then those stanchions were embedded into the 3.5 meter thick raft, and then shear studs connected to those columns to affect the transfer between the two systems. This is how we've built now 2 buildings. Since then, we've been back in the laboratory testing alternative connections, and the one that's proved out to be, we feel, better is kind of the opposite of this, if you will, and that is much more like you would build a reinforced concrete core wall, where vertical reinforcing steel dowels are placed protruding upwards from the mat that would then be embedded inside the first lift of the SpeedCore wall, creating what effectively could be described as a non-contact lap splice. But what we've discovered through the research is, because of the very efficient and effective confinement of the concrete via the cross ties in the plates, that splice condition works very, very well. It's very robust, it's very ductile, and the future jobs that we're now designing, we're going to use that connection methodology where we build the pile cap or the raft or whatever foundation element that we're building, inclusive of vertical protruding dowels that then extend upwards into the first lift of core wall and do that connection in that manner.
thanks, Ron. Through Rainier Square and all the other projects, have you and the team measured sort of the carbon difference on this solution compared to the traditional RC core?
So we have, and I'm going to tell this a little facetiously, but hopefully you'll get my dry American humor. Uh, the spin is that, of course, it's far more carbon effective because we're using recycled steel materials. We've eliminated all the rebar. We've reduced the amount of concrete by upwards of 30%. And I can go on and make a big list of all the things that are better, inclusive of the fact that we're able to build the building 10 months faster or 30% faster than otherwise. All of these things add up toward a very friendly reduction in carbon consumption. The truth is, we don't really know. And why? What I mean by that is on the reinforced concrete side of the equation, no one, to my knowledge yet, has quantified precisely, for example, the carbon associated with the formwork system, the recycling of the formwork system, the operations of the formwork system, the embedded steel plates, and the labor involved with the fact that 10 to 15% of them are always misplaced, and so on and so forth. If you really want to get into a scientific assessment of like for like, it's not actually possible today because the data doesn't exist on the concrete side. But at a very high level, if we want to spin it really hard, we'll spin it very hard in favor of SpeedCore being much more carbon friendly than a reinforced concrete wall.
Thanks, Ron. For Rainier Square, what were the sort of site shift hours to achieve about 66 floors in 10 months?
Yeah,
Um,
so yeah, good question. So I kind of high level give you some facts that I remember. So there were two erection gangs. The one erection gang focused strictly on the core. They were able to erect a tier of the core, meaning 2 floors of the core, in 4 days. They worked a 4-day week and they went home. The horizontal erection gang that erected the steel columns and the steel beams and the metal decking for the floor, etc., they worked 6 days a week, every week, to try to keep up with the core, meaning we could go much faster with the core vertically than we could go horizontally with the steel floor framing. So if in round terms you say the vertical crew worked a 4-day week and the horizontal crew worked a 6-day week, that's close to the truth.
yeah. Um, I think for Rainier Square, the floor starters, they were all straight development lengths. What are the other options if you don't have that sort of space?
So I think the question relates to the reinforcing steel that connects the SpeedCore wall to the floor slab. Is that?
Well, yeah.
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 Yeah. So we debated a number of ways to make that attachment. In the end, it was chosen by the contractors to drill the holes and place the rebar as you saw in the one image that I shared. An alternative that we discussed was to pre-weld onto the outside face of the SpeedCore wall panels Lenton half couplers, essentially threaded couplers that are half couplers that could be welded to the outside faceplate and then the reinforcing steel screwed into the half coupler. Um, that was not selected because of the concerns of during handling that the half couplers would be displaced or damaged. So instead, they opted for the holes and the rebar set through the holes. If in all of the cases we've designed so far, we haven't had any issues with the development length question. But I suppose if you had a thin enough wall, that could be something to think about, but I'm sure there's a crafty detail that you can come up with to solve that problem. Noting in the cases where we used that particular methodology, the demands are comparatively light, where we had heavy demands. For example, at the street level slab, where there's a very huge shear transfer from the core out through the street level diaphragm to the basement walls. In that case, a lot of the connection, a lot of the shear transfer was handled more directly through the steel beam connections to the wall and more robust steel beam connections, and handled that load transfer and distribution out of the core into the floor slab, into the basement walls more through steel than through reinforcing steel.
Thanks, Ron. And then I'll probably make this the last question because we're a bit over time. I'll try to lump a few probably construction related ones together. Um, Craneage. So obviously it's different to a climbing core and the Nasi. How is craneage managed? And also in terms of delivery, these are quite big elements. How is it managed in the CBD environment? And did you have any issues with craneage for any of these sites in terms of windage? Because these effectively act as like a big sail.
Well, all really good questions. Yeah, we could spend a couple more hours talking about construction issues. I'll just give a few highlights. Shipping is a significant issue to be paid attention to. In all cases where all these buildings have been built, load width has been restricted. And so that sets, in some cases, the size of the panel in terms of what you're able to ship effectively. So shipping is a big thing to think about. In terms of craneage, a number of issues with regards to crane. The easy one to think about is pick weight. These typical panels weighed, in rough terms, 9 to 10 tons. So that kind of gives you a starting point. But of course, some of the specialty panels around the outrigger connections were heavier. So specific consideration about crane picks and crane pick weight is important. Another consideration that's really important with regards to the crane are the crane tie-ins. As you go to jump the crane vertically, is the crane tying into the unconcreted core or the concreted core is a question. It's a design question. It can be designed either way, but it's something to be considered in terms of how and where you're making your crane tie-ins and where they occur with regards to the concreting operation. Yeah, lots more to talk about there, but that's another seminar.
Thanks, Ron. Appreciate it. I think on that, I mean, there's a few more questions. I think Engineering Museum maybe send them through and we could include that in the recording as like a Q&A, but just want to thank you for your time and presenting to the engineering body here in New Zealand.
I
Really
appreciate it.
appreciate it.
And I guess I'll extend the offer and invitation. Anybody who has any additional questions or wants to talk to me directly, you're welcome to reach out. The best way to get a hold of me is via my email. And my email is very simple. It's my initials, rk@mka.com. And to the extent you want to reach out, again, my email is rk@mka.com. Happy to talk to you about any other details or, talk about a project, whatever can be helpful. Happy to do it.
Thanks, Ron. Much appreciated.